Hello and welcome. In this video, we're going to look at how to measure the phase lead of this RL series circuit. So the phase lead is the difference between the source voltage and the voltage drop across the inductor. So that's what we're going to do. We're going to grab our oscilloscope. That's the fourth one on the sidebar over here, or it's in your simulate instruments, and the fourth one down is your oscilloscope. We'll place that in our screen here, and channel A, positive lead, goes around our source voltage, so we'll drag and drop that over there. And the negative side goes anywhere after our source on the negative side there, so we can place that down there. The channel B needs to wrap around our inductor, and so we can measure that, and this one can be kind of tricky, but you could place it anywhere above your inductor. Anywhere up here would be just fine for the placement, and they actually give you this little line to pin it to there. And then the negative side goes to the bottom side of the inductor. Anywhere after the inductor there is fine, so we can place it on our little line that they gave us here as well. So the positive side of channel B, I usually like to make it a different color so that I can see the difference between my source voltage and my inductor voltage. So I'll right click that one and change the segment color to, say, a blue color. We'll OK that out. And so now we've got blue lead leading into channel B, and so we're going to see the blue waveform is the inductor's voltage. So we'll double click on this, and we'll hit play. We get a really small waveform. It's all cramped in there. So we're going to take our time base and we'll scale it down. Click once in here, and I'll give you these arrows, and you can just scale it down until you see a nice clean waveform. And then we can stop the circuit there and move it back just a little bit so we get a full view. And at this point, we're ready to measure our period and our phase difference here. And so we are going to do a couple of time measurements. We got two lines here that we get to use. The first one, we can take channel 2 probe, right click it, and go to the next Y max. And we see that that's on that red line top peak. And that's where we want it. And we can click once and grab this blue line over here, their blue probe, right click and go to the next Y max there. And now we see that it's on two separate peaks there, one peak apart. And that's our full cycle rotation. So that's going to be our period. So we're going to write down that number. And specifically this number right here, 125.7. And that's in microseconds, right? And that's our period, so that's our time, t. And we also need the change in time. We need the difference between the two time intervals. And so specifically the difference between the two waveforms that we have here. And we do see one waveform is sitting over here, slightly in front of the other waveform. And I say in front of because time happens first over here, and then as we progress, time continues moving forward. And so as far as time goes, that blue waveform showed up first. The red waveform showed up second, which means that our inductor's voltage is leading our source voltage. And that's what we're talking about when we talk about phase lead. So we need to measure the other signal, and we want to do both of these measurements, the difference measurements. We want to do them on the Y or the x-axis line, and that's that white line down the center. Right, so that means that we want to take our, let's do our yellow probe over here because it's going to be a phase lead. So we can push this one off to the side here. And our yellow probe can come up here, and then we want to right click and set the Y value backwards to 0. Right, we're going to set a 0 in here, and that's going to set us right on that 0 axis line there. And that's going to be our most accurate reading for this because of our sampling of our oscilloscope. So if we measure from the two peaks, it's not going to be as accurate. So now we can grab our other waveform, and we see it's still following that red line here, and we don't really want to follow that. So we can right click in the field and select trace, and then we'll transfer to channel B. And that's going to allow us to measure channel B's waveform. And so now we see that when we move our blue line here, it's still following channel B. We do not want to touch the yellow probe line because that's set perfectly on that channel A waveform, right? And so now we grab our channel 1, right click, and we can go to the next Y max since we're going backwards towards that other probe line. And we'll set 0 here and set OK. See, and we should be really close to each other right here. We want them on that same rising edge there to compare. And we got 24.965 out of that. So that's our change in time, 24.965 microseconds. So now we get to plug that into our waveform equation. And that means that we take the change in time and divide it by the time that we have for the total cycle. Those are the two values we just measured. And then we'll multiply it by the number of angles that we have in a full circle rotation. And that's what this waveform is actually representing. It's representing the rotation of a circle. And so when we talk about phase angle, we're talking about the rotation of a circle. And so this is the phase lead. So we'll take the time difference, 24.965. That's in microseconds. They're both in microseconds. So when we divide those two out, they're going to cancel those microseconds out. So we can even leave it off because we know it's going to cancel. And we'll put 125.7 on the bottom, technically microseconds, but they cancel out. And then we multiply by the number of angles that we have. So multiply by 360 degrees since we have 360 degrees in our full circle. And that gives us 71.5. And that's kind of what we expected from that. 71 degrees, and that's an angle magnitude. let me know if you have any other questions.